follow gamma distribution, alpha comma beta. We have the PDF of the gamma distribution given to us, and then we want to find the MGF, the mean, and the variance. Now, to do this, now let's find the MGF, and we have the general rule for the MGF to be mx of t equal expectation e to the power of tx. Don't forget that this is a continuous distribution. So we have that to be e to the power of tx. This is going to be from 0 to infinity, looking at the constraint, times the PDF of the gamma distribution, 1 over gamma A alpha, beta to the power of alpha, x, alpha minus 1, exponential negative x over beta. Now, taking out the constants, we have 1 over gamma of alpha, beta to the power of alpha, 0 to infinity. Now, looking at the two exponential sign, this and this, you can see that both have the power of x. So we can combine them together to be exponential x. Factor out this x, we have t minus 1 over beta, okay, multiplied by x to the power of alpha minus 1. Now, by doing this, we can rewrite this equation as 1 over gamma of alpha, beta to the power of alpha, 0 to infinity, okay. Now, rewriting this, so here I'm going to have exponential negative x. So I'm having 1, okay, minus t beta by taking the fraction beta, x alpha minus 1. Now, looking at this kernel distribution, here we can see that here we have 1 over gamma of alpha, beta of alpha, multiplying both the numerator and the denominator by beta over 1 minus tb to the power of alpha, gamma of what? Alpha, okay? We have beta 1 minus tb. What is the condition for multiplying this? Now, we have this general rule of gamma distribution, which is going to be explained in the next video. Here, looking at this general rule here, if you want to, this is like a PDF of another gamma distribution, okay? So here we have this as the beta, which is negative x over this. You can take the reciprocal of this, and here we have this gamma of the alpha function. So this is going to be the beta function, okay? So now taking the reciprocal, this is what I have here. So it's just like this, gamma alpha, beta to the power of alpha. So this is going to be my beta to the power of alpha, and this is going to be my gamma to the power of what? Alpha. So it's like having the same thing. Now, so here I'm going to have 0 to infinity exponential negative x over beta 1 minus tb. So what I just did, x alpha minus 1, what I did is just to rewrite this expression as this, which is still the same. Now, here I'm going to have 1 gamma alpha beta to the power of alpha. This is the same thing as beta to the power of alpha gamma alpha divided by 1 minus tb to the power of alpha. That is, I'm rewriting the numerator, multiply by 1 over beta 1 minus t b all to the power of alpha gamma alpha is 0 infinity exponential negative x divided by beta 1 minus t beta alpha minus 1. Now looking at this is a PDF of a gamma distribution. Okay, but the parameter is quite different from the one given in the question. Now this is going to be a PDF, and don't forget that PDF sum up to what? 1. So we're going to be left with this information. So now here I'm going to have 1 gamma alpha beta multiplying by beta to the power of alpha gamma alpha all over 1 minus t beta to the power of alpha. This cancel out this cancel out this. So finally, my mx of t, which is the MGF of the gamma distribution, is going to be 1 divided by 1 minus t beta to the power of alpha. Or you can say that 1 minus t beta to the power of negative alpha. This is the MGF of the gamma distribution. Now, we want to find the mean. Just like in my previous video, to find the mean of the MGF, what you need to do is just to differentiate. Okay, if you want to find the variance, you take the second moment and you take these differences. Now, doing the same thing here, by finding the mean, it's like finding the first derivative or the first moment of the MGF. Okay, so we want to differentiate with respect to t and set t to be equals to 0. Now by doing that, differentiating this with respect to t, just bring this to the back and subtract this from 1. That's just what we need to do. So here, by differentiating, it's like you differentiate what is inside the parentheses too. So you have, here we have alpha, negative alpha, multiplying negative beta. Because if you differentiate TB, you have beta with respect to t. Okay, so we have 1 minus t beta negative alpha minus 1 by setting t to be 0. So setting t to be 0, this is going to give us 0, and 1 to the power of negative alpha minus 1 is still going to be 1. Here I'm going to be having alpha beta. So this is my mean. Now finding the variance. For the variance of x, we have this to be the second moment, okay, the second derivative minus the first, all squared. So now we need to calculate this. Now by calculating this, that means we're going to take the second derivative of the MGF function. Now taking the second derivative of this expression before we set t to be equals to 0, okay? Now this is going to be negative, okay? We have negative, that is bringing the negative alpha minus 1 minus alpha minus 1. Why do we have the negative? Is because if you differentiate, so here we have alpha beta 1 minus tb negative alpha minus 2 times beta. Now this is going to give us alpha beta, okay? Here we're having alpha beta multiplying beta. So we have alpha beta squared, okay, alpha minus 1, 1 minus t beta negative alpha minus 2. So that means no parentheses here. We only have one parenthesis. Good. Now, simplifying this further by setting t to be equals to 0. So we're going to have alpha squared beta squared plus alpha beta squared. Don't forget we have this, we have this negative sign here. So this is the second moment. So finding the variance of x, so it's going to be alpha squared beta squared plus alpha beta squared minus the first moment, which is what? Alpha beta all squared. So this is going to be alpha squared beta squared plus alpha beta squared minus alpha squared beta squared. Cancelling out these two, finally, my variance of x is going to be alpha beta squared. Thank you very much for watching my videos. Please don't forget to subscribe. See you next time.